Day 121, Honors Physics, Mirrors and Ray Tracing, Part 2. So we'll be using ray tracing, or rays, to depict or to model the movement of light, to explain how images are formed in mirrors. In particular, we're talking about curved mirrors here, concave and convex. And it'd be best if you use a ruler. In class we'll be using a ruler, but because of the way my iPad's set up, I really can't use a ruler when I'm doing the explanation here, but I think it'll work out pretty well. Anyways, in this first diagram here on the left, this diagram, these little hash marks back here represent the back of the mirror. The front side is the reflective side. I cut and pasted these diagrams from some book, but these O's don't need to be here. I'm not sure why these little O's are there. You can ignore them, that one and that one. And this is a diverging mirror over here. It's convex. I'll get to that in a minute. But whenever I do these, or as we do them in class, traditionally or conventionally, we'll do these from left to right. You can do from right to left, but you'll see as I go along here, I'm going to be doing everything from left to right, so I recommend you doing the same thing in class. But every mirror has a focal point, or curved mirrors do, and essentially this first example here, number one, this rule number one, is really how you would find the focal point of a concave converging mirror. For example, what we're saying here is light coming in parallel to the principal axis. Now the principal axis is this line right here that essentially splits the mirror perpendicular or horizontally through the middle of the mirror. So that ray of light that I just drew coming in towards the mirror is going to reflect. I'm not going to draw normal right now because that's going to really clutter our diagrams, but you could draw normal. But the bottom line is, for a curved mirror, concave mirror like this, we will now understand that if a light ray is coming in parallel to that principal axis, that it will reflect. That's supposed to go through F. Let me see if I can do a better job of hitting F. There we go. So there's a ray of light that comes in parallel to the principal axis, and it reflects through F. And I can draw a bunch more. I don't need to, but I'll draw a couple more just to show you. In the real diagrams, we won't be doing multiples of these. We'll usually just do one of these per diagram. I could have one that's coming in on the lower side of the mirror. That's supposed to be parallel to the principal axis, and it'll come out through the focal point. So all those rays of light coming in parallel will reflect through the focal point. Now the same thing is true on the right here with this convex mirror, except for, once again, light will reflect off a mirror. It will not pass through the mirror. We have a ray of light coming in parallel to that principal axis, but it's going to bounce to the left. But based on the angle there, and if you drew normals, bottom line is, the way you figure it out is that this reflected ray will line up with F. In other words, if I draw a dashed line right here, this will be the reflected ray. It lines up with the focal point. Really what we have here in the second mirror, this convex mirror, is a virtual focal point. F is a virtual focal point, and when we actually do problems numerically, we'll have a negative focal length for that mirror, measuring from that, where that principal axis, this principal axis here, intersects the mirror, like right from this point right there. If you measure from there to here, that's the focal length. And for a diverging mirror, that will be a negative number, like negative 0.5 meters or 0.25 meters or 25 centimeters. A lot of times we'll be using centimeters. Okay, so I can show you a couple more here. I'll just do one on the lower side. I'm not going to do 3 or 4 like I did on the other one. But if I have another ray of light coming in parallel to the principal axis, it's going to reflect off of that mirror such that its reflection lines up with that focal point. So you can use those dashed lines. Whenever I'm working behind a mirror, I like to use dashed lines. But anyways, experimentally, we'll be doing this in the lab to actually find the focal point by shining light towards a mirror and seeing how it forms that focal point, shining in parallel beams of light, and verifying and measuring the focal length. All right, rule number 2 is really just the converse, or the reverse, of rule number 1. And that is a ray of light coming in through the focal point. Here's a ray of light coming in through the focal point, hits the mirror, reflects such that it comes back parallel to the principal axis. I could draw a bunch more, but I'm not going to, because in the diagrams we'll be doing in a little bit here, we'll be doing one of these per diagram. We'll be doing step 1, then step 2, and then step 3, not always in that order, but usually just one of each for a total of 3 rays per diagram to help us locate and describe how mirrors form images. So here's the other one. This one works because it's a diverging mirror. Let me try to do a better job there. I want to aim that towards F. So I have a ray of light. It's not going to go through the mirror. Once again, these hash marks on the back there represent the back of the mirror. That ray of light is heading towards F, but it won't get there. It'll hit the mirror and reflect this way, parallel to the principal axis. I can draw more. I'm not going to do that. That's rule number 2. We'll come back to that with an example here in a minute. Let me go on to rule number 3. All right, rule number 3, and there's nothing magical about 1, 2, and 3. You can do these in any order. Bottom line is there's just 3 rules. Each one rule is different, but they're useful in finding the location of images. In this one, we're going to have an incident ray through the center of curvature that will be reflected back onto itself. Now, the center of curvature is twice as far from the mirror as the focal point. That is in one of the rules or the equations that I laid out yesterday. Now, the equation looks like this, and we'll be computing these in a few minutes here. F equals 1/2 r, the radius of curvature. So bottom line here is I have to extend my principal axis for this, well, both of these mirrors probably. So if I make this longer here, and I have my focal point already labeled, and let's say my focal distance from the mirror here to there is whatever, 5 centimeters. I need to then mark off that distance again. Say out here, it's another 5 centimeters. That's my center of curvature, C. Because my radius of this mirror would be my focal length would be half that radius. The radius would be from C along that principal axis. So it would be from here to there would be the radius of curvature of that circular part of that mirror. All right, anyway, it says that a ray of light through that point. So I'll just use blue in this case so you can see it better. There we have a ray of light. It's supposed to be straight. Coming in, it hits the mirror, and it hits the mirror straight on, basically perpendicular to a tangent that would be drawn there. So it would be along the normal line, and when it reflects, it would be reflecting right on top of itself because the angle of incidence is 0 degrees, so the angle of reflection is 0 degrees. You'd have a ray of light that comes right straight back, this way, bounced back on top of itself. And once again, I could draw a bunch of those. I'll just draw one for now. Same thing is true over here for the convex negative mirror. I will need to extend the principal axis and then estimate my center of curvature, which is about twice as far, well, not about, it's exactly twice as far from the intersection of the principal axis with the mirror. So that's C. And I'll draw a ray of light. Once again, you can draw it from any direction. It's not going to go through the mirror, but it's heading toward C in a straight line path. Whoops. And then, but it doesn't go through the mirror. It hits the mirror and reflects straight back. So the reflection comes back this way, right on top of itself. So now let's show you how that actually applies to solving problems and locating images in, quote unquote, in the mirror. So here we have a converging mirror. The back side is back here. I don't like the shape here. But once again, this one's nice because I'm indicating the back side of the mirror. So the shape, that's the reflecting surface, is like this. But what I like here is they've labeled points F and C. F is half as far from the mirror as point C. Now there's 2 basic ways to solve these problems. We can do them by calculation and by ray tracing. I'll do this one first by ray tracing, which is the less accurate, but it's the more descriptive visually on how images are formed. So in this case, we have an object. And you can use anything as an object, a person's face, a dog, a cat, a tree, but we like to keep it simple. At least I like to keep it simple. And I'm going to use a candle. Sometimes I use an arrow or a pencil. But in this case, it says the radius of curvature is 40 centimeters. That means it's 40 centimeters from point C along this principal axis to the mirror right there. That's 40 centimeters. That means the focal length is 20 centimeters. So I already know that because the focal length is equal to, in other words, F. And I usually use little f. Little f, focal length, is 1/2 the radius of curvature. which is given as 40. So 1/2 of 40, so F is 20 centimeters. I'm already using some of the space. Well, I think I'm okay. The object, and I'm going to use a candle as my object. And here's how this is typically done. The object, it says, up here, is at 30 centimeters. The focal length is 20 centimeters. And the center of curvature is 40 centimeters from the mirror. So I'm going to put my object, which is a candle, I'm going to put my object right here. My object is going to be a candle. It's halfway between F and C. So let's say it's a lit candle. That's supposed to be the flame of the candle. Now, when you're trying to form an image or trying to determine where the image of an object is, it has to be something that either is reflecting light or giving off light. The candle's nice because it gives off its own light. An actual image takes millions and millions of rays to form. But there's the little trick here. We can use the 3 special rays from the previous page. From typically the top part of the object will help us to locate the entire image. So let me show you and then explain it more fully as I go along here. This flame here on a candle, I'm going to start to use black as my rays. This flame, the candle burning, is giving off light in millions of directions, like this way and this way and this way and this way and this way. And some of that, so there's also some light that's reflecting off the body of the candle, the waxy part. But I don't care about 20 million rays of light that's given off by the candle. What I care about, I'm going to erase all those, is the 3 particular rays that were on the previous page, and that is the one that comes in parallel to the principal axis. I called that rule number 1, but it doesn't really matter what rule it is. I have at least one ray out of millions I can draw that come in parallel to the principal axis, and when that hits the mirror, it reflects through F, like that. All right, and then rule number 2, out of millions I can draw, but these aren't random ones. These are specific rays that help me solve problems quickly. A ray of light that comes through F, hits the mirror, and bounces out parallel to the principal axis. Now, my rule is you got to draw at least 2 of the 3 rays. The third one here is going to be hard to draw. In fact, it's almost impossible to draw because my mirror is too small. And I have some inaccuracies already. You'll see that as I go along here. But bottom line, you only need to pick 2 of the 3. The third one, if you had enough space here, would have been a ray of light that would be lined up like this, hitting the mirror like that. I'm going to erase that because my mirror is too small and there's going to be some great inaccuracies here. We'll do the calculations to be more accurate. But bottom line is you draw these 2 rays. 2 rays are sufficient. And where they intersect, in this case they intersect right here. That location, which I'm depicting with a red dot, is mapping the image location of the flame of the candle. That's where the flame of the candle image will be. It's not the actual candle, it's the image of the flame. And it always turns out that the base of the candle is always on the principal axis. In other words, and I'll explain this as it goes along, this is going to be and if I kind of just sketch it in here, that's going to be the flame of the candle if I expand it out a little bit. And the body of the candle is going to be like this. So my candle, if that's the wick, is going to be, the image is going to be upside down, as I will show you in class if I haven't already. So this right here is the image. This over here is my object, what I started with. And I've located the image by ray tracing, just by finding the flame or the top part of the image, which is the most critical part of the image to find. And then you reconstruct the rest of the image, which is always connected to the principal axis. The bottom part of the image is always on the principal axis. So here's the thing, and we'll practice this. You have to describe this image in 3 ways, and it's outlined up here, A, B, and C. You have to tell me whether this image is real or virtual, where it's located. By diagram, you'll have to approximate that, and what the magnification is. In this case, for example, the answers to the questions A, B, and C, based on my diagram, which we will fix with the calculations, or in other words, become more accurate with the calculations to see how well we did with the diagram. I know this is a real image. So based on the diagram, my answer to part A it's real. It's real, and there's two huge clues. First of all, it's flipped. It's upside down. Anytime the image comes in upside down like that, it's real. The other reason, or the real reason why it's real, sorry about using that word twice, is that it's actual light that's converging at that point where I found the image location of the flame. I'll expand on that later. Part B is going to be now an approximation based on the geometry. I know point F is 20 centimeters. The image, or the object, was at 30 centimeters. The center of curvature is at 40 centimeters. So my image is at about, 42 centimeters. So my image location, and I use the letter Q. So I will say Q, image location, is about, I should use the wavy equal sign because this is not exact science here, especially without a ruler. Q is about 42 centimeters. And then part C, what's the magnification? In my case here, it looks like it's about a 1-to-1. M looks like it's about 1. In other words, if the image looked twice as big as the object, I'd put a 2 there, or 3 if it looked 3 times the size. Or if it was half the size, I'd put a 1/2. And you're going to find out that these diagrams are sometimes fairly inaccurate. But now, we're also going to do these by calculation. For example, the main thing that you will do by calculation to verify this, and you don't have to do every problem both ways. Most of the problems on the homework and the test will be done with calculations, unless I say you have to do the diagram. The diagram is optional, but if you want to check it, you use the diagram. But it's also a good visual as to what's going on here. This first one is explaining how an image can be upside down with a concave mirror, as I've been showing you in class, or I will show you in class. But mathematically here, the main equation you start with is 1 over f equals 1 over lowercase p plus 1 over lowercase q. In this problem now, mathematically, I was given f, or I found it out to be 20 centimeters, half the radius of curvature. And we can stay in centimeters. The object distance was 30 centimeters. So I can simply solve for q. I'm going to pause and do that math. All right, and that came out to be 60 centimeters. So my diagram is way off, which happens fairly often, partly because I don't have a ruler or a straight edge. But Q should have been 60 centimeters. In other words, my image should have been further to the left. I estimated on the diagram it was 42 centimeters, just beyond C. But it should have been way out more towards the left. But here's the calculation. And this is an important number right here. It's not the end all. Well, it sort of is. But if you didn't have the diagram, and you still had to describe the nature of the image. So up here when it says describe the nature of the image means I want 3 things. I want these 3 things every time. I want you to tell me whether it's real or virtual. So let's say we didn't do the diagram yet. How can you tell simply by that Q is equal to 60 that this is going to be a real image? So, well, it's real because, just doing the calculation, since Q is positive. Q is positive. If Q is positive, the image is real. So that's another way to tell if the image is real. Part B. Well, part B we have Q is 60 degrees. Or 60 centimeters. That's the accurate location of the image if we had the perfect system and a perfect diagram. Then part C, what's the magnification? Well, the magnification equation is M equals negative image distance over object distance. So it would be negative 60 over 30. I'm going to do this off to the left here. M is negative 60 over 30. I mean, you can do that in your head easily enough. That's negative 2. And what is the meaning? And there's no units here because it's 60 centimeters over 30 centimeters. The units cancel out. But M is negative 2. So the image should have been twice as big as the object. And the negative means flipped. It means flipped. So this is our first introduction to ray tracing to find an image and calculations to find an image. And you'll see the calculations are the preferred way unless you're forced to do the diagrams, which there's a place and a time to do them. For now, it's going to be when I force you to do it, and I want you to practice those, and we'll practice those more in class and tomorrow. I'm also noticing back with my diagram problem where I put part C, m equals -1. If I go back up there, I should have said up here, where I have m equals 1, I should have said m equals -1. So I can put the negative in there now to fix that. Whoops. -1. So my diagram should have said -1. The negative indicates that it's flipped. The object was up right side up, the image is upside down. And you can see my magnification estimation was way off. It should have been twice as big if I did a perfect diagram.